application of the second derivative is curve sketching occurs in locating the max and min. So we're going to kind of also look and see how we can we're going to use the second derivative to also help verify their max and min. And we talked about this yesterday. When they're concave up and they're concave down, we get that from our second derivative. And if they're concave up and concave down, that also signifies that they're going to be a max or a min. So that's just kind of, that's why this is so short. This is just selling the point, the idea that the second derivative can also signify if it's a local max or min. Okay, so because if it's concave up, then it's going to be a what? Min, right? Concave up means it's a bull, so it's going to be a min. Concave down means it's going to be a max. Okay, you good, Zach? Yeah. Okay, zip it. Okay, so curve sketching occurs in terms of local max and min. So this was just telling you that f prime of c is 0. And if that f double prime is greater than 0, then we know it's concave upward by yesterday, therefore signifying it's going to be a minimum. Okay, and so going forward, this is essentially the second derivative test. Your f prime of c is 0, and your f double prime of c is greater than 0. That means a local minimum. Because if it's greater than 0, that means concave upward, which creates a local minimum at c. C is still the critical value. So you know that our critical points from the first derivative, if you put that critical point in the second derivative, greater than 0. Does that make sense? So if, once we figure out the f prime of c critical values, that value greater than 0 means a minimum. And the double, second derivative. Yeah. Okay. Oops, I grabbed the wrong paper. Okay. Bless you. All right, and that's the lesson today. That's the definition we're just doing today, and we just have 2 examples now. Okay, so that's it. So let's look at it here. Does everybody have this as much as they need it? Okay. All right. So example 1: find the local max and min values of f of x equals x cubed minus 12x plus 5. Okay, so the first thing we're going to do is we're going to find f prime, which is 3x squared minus 12. Okay, then we're going to notice that I'm going to find the zeros, so we're going back to definition. I want to find this, okay, that value, which we pull the 3 out, then you see we have a difference of squares. So your CPs, critical points, are 2 and negative 2. Okay, so now we're going to find the second derivative and plug those in to see if they output a positive or negative number. Okay, so second derivative is simply 6x, which makes it very easy for us to see that f double prime of 2 is 12, so that means a minimum, right? Yeah. Min or max? Hold on. We put it in, we got bigger than 0. Yeah, so it should be a min. Okay, and then f double prime of negative 2. Get negative 12, so that's a max by the definition. Right. I have it backwards in my notes, but I know that we're good. Okay, to figure those points actually out, we would take 2 and we plug it into the original. So what is that local min or max? So just doing that quickly, if I plug 2 in up here, so the point we're talking about for that min is 2, so that's 8 minus 24, negative 16 plus 5, negative 11. So 2, negative 11 is a min. And then our max, a local max, is negative 2, which would be negative 8 plus 24, 16, Negative 8 plus 24. 21. What? The 2. I put positive 2 into the original function to get the actual point on the graph.
And that's how you got 11?
Yeah.
Well, then what'd you do with the 12?
The 12 just told if it's a max or min by the definition. So being a positive, it means it's a min.
Okay.
And that min point is what we're fitting. I forgot, Emily, we plugged 2 in to get the actual point.
Okay, that makes sense.
Yeah. Yep. And so then negative 2, I think, what was that? 21, I think? And my notes are all messed up, it looks like. But anyway. Okay. So we're good there. All right, example 2. And example 2, we're going to graph it as well. All right, so find the maximum values of y equals x4 minus 8x cubed. Use these together with concavity and points of inflection to sketch the curve. So we're finding the max and min, we're finding the concavity, and we're finding the points of inflection. Okay, so that's what we want to do. Remember, your points of inflection, you have to use the chart to figure out when your concavity is changing. When your concavity changes, that's a point of inflection, and that's a second derivative. And that's what we were kind of choppy on yesterday a little bit. Okay, so first derivative, we'll start with that. We get 4x3 minus 24x squared. I can factor that. I can take out a 4x squared, which gives me x minus 6. So you see that our critical points are 0 and 6 here. Okay, so now we're going to find the second derivative. So, like, long story short, like with the first derivative, I could take 0 and 6, and I could test for increasing and decreasing, do all that to figure out the max and min, but we're using the second derivative to do that quicker. So we don't have to test those sections for increasing, decreasing to get that specific answer. Now, if the question does ask the intervals where things are increasing, decreasing, you will still want the chart. But this can jump us ahead to find the max and min a little bit faster. So y double prime is 12x squared minus 48x. Okay, I could factor that if I'd like. 12x gives me x minus 4, which we'll use for our points of inflection, right? So we still plug the 0 and 6 in. So if I plug 0 in, do I get positive or negative? Ends up being 0, right? So if it's 0, what do we put for that? So if we put 0, yeah. If we put 0 in, then that should be, it's neither. Because it doesn't meet the restrictions for either. Yeah, so no information. So plugging in 0, I got 0. There's no information for me that's a max or min. Okay, plug in 6, we get a positive. So let's put this here. Sorry, I'll write y double prime of 0 equals 0, no info. Of 6. That gives us, if we want the actual number, 72, 144. So that means a min, right? So we get a min at 6. Okay, so we can get that point if we want. I'll save that for later just because that's kind of bigger numbers I don't want to deal with right now. So we know we have a min at 6 something. I'll do that in a second. Okay, what else to tell us to find? Oh, concavity. So we have to do a concavity. We want to look at concavity at these sections, so 0 and 4. So 0 and 4 is the chart we're going to want. Like we can put this. It's fine. Doesn't matter how you do it. But I do know I want to go x less than 0, x between 0 and 4, and x bigger than 4 is where I'm looking at, those 3 sections for concavity, right? Just like we do for increasing, decreasing. Where did I get the 0 and 4? From right here, right? It's the critical points for the second derivative. And so this is where it doesn't matter to me, but I'll write the factors, it's fine. I don't have room here, but and then it's what is f double prime, and then does that mean up or down? We'll just do these three sections here, sorry. So x less than 0. So if I plug in a negative number into here, what do you get? Positive, because it's, right, it'll be negative and a negative, so I get a positive.
Wait, would it be, is it 12 times negative times another negative, so wouldn't the first one be positive though?
So
Oh,
this is
never mind.
pieces, yeah, but you're right. The outcome's positive. So I'm just doing it piece by piece. Yep, 1, positive, negative, so negative. And then bigger than 4, it'll be positive all the way across, right? Okay, so remember, if you get positive, what does that mean? Which means concave up. It does mean increasing for the first derivative, but second derivative means concave up. Okay, so that fourth section that I ran out of room on, it'll be concavity, and that's a CU. So it's CU, CD, CU. So it changed at 2 spots. So both 0 and 4 are points of inflection. So understand, we have 0, 4 as points of inflection. What was our points of like your increasing, decreasing points? 0 and 6. So we have all these points of information now. This is how we're developing our curve sketching. We're getting all this information that we can put all this stuff down. Okay, let's see if there's anything else we need. Nope. So we know just for writing an interval notation, we know it's concave up from negative infinity to where? 0 and 4 to infinity. And we know it's concave down between 0 and 4 with your interval notation. Okay, my next slide, I have the graph. Okay. So remember, we can think about a lot of things. Like I hope that when you're seeing this stuff, I know it's hard to put all together right now in your head, but I think that you can see that being concave up means that we're looking like it's going to, the end behavior is going to be going up, which it is because it's even, right? So even is going to mirror itself on the ends in terms of its behavior. Okay, stuff like that. So here's what the picture looks like, and let's see if we can kind of identify everything we figured out. Okay, so everything we figured out. So 0 wasn't a max or min, but it was a what? A point of inflection. So that's why it was a critical value. It switched concavity there, but it wasn't a max or min because it continued going upward. So that's kind of the weird point. Look, that's kind of weird. Concave up to concave down, but no max or min. That's why there's no information there. Does that make sense? Okay, and then see this one was good. So here was the other inflection point. So we went from down to up. So just a little twist there. Okay, there's our minimum we knew, 6. So it was negative 432 is that big number I was expecting. And then we went back up. So there's a 6. There's a 0 that we got for our critical values. 0 was a no information, as you can see. Why? 6 was a local min. Okay, we had our points of inflection at 4 and 0. Okay, and then if we did our increasing, decreasing chart, it would have been, this is an example of decreasing and decreasing. So we would have done that, we would have got decreasing and decreasing, which would not have been a max or min point. Okay, and then we have decreasing to increasing. Any questions on building that there? Okay, so that's the kind of thing you're going to have to sketch something like that on your test algebra calculator. That's the point of this unit, curve sketching. Okay, all right, so I'll pause this, and I'd like to do at least 1 or 2 problems with you guys from yesterday, and then I'll let you guys have your time.